Hi folks, this is Physical Science Module 15, and we're going to talk about light. And a lot of this will be review here at the beginning because we've talked enough about waves this year that you are aware of some of the properties and qualities of light. So first thing, light is electromagnetic waves. They're transverse waves, meaning that if they're traveling toward you from me, then they oscillate perpendicular to that, right? And so when something's oscillating like this and traveling like that, then you get kind of this curve, right? Like this. And so when we look at a transverse wave, and if that wave is light, for example, we can see that the distance between two analogous parts of the wave, meaning two crests, which is what I've drawn here, or two troughs, or two places where the up cycle is about to start. But here, crest to crest, we have the measure of the wavelength, which is just the distance between two crests or two troughs, for example. And the wavelength of light, as you learned last chapter, determines the color or quality of the light. And we'll talk about all the things that wavelength can determine about light shortly. But color is one of those things. And then the amplitude, which is from the node to the trough or the node to the crest, that distance, which would be the same either way. And the amplitude of a light wave determines its brightness. So the bigger the amplitude, the brighter the light would appear. So a few questions about light, which probably you've already learned in the past. So does light need a medium to travel? You guys learned that sound waves need to travel through air or a liquid or a solid or some kind of medium. Light actually does not need a medium to travel. It can travel through the vacuum of space, right? So we know sunlight reaches the Earth after traveling just over 8 minutes through the vacuum of space. Light travels at its very fastest. In fact, the fastest thing that we know of in the universe is light traveling in a vacuum. And when light is traveling in a vacuum, its speed is 3.0-ish times 10 to the 8th meters per second, right? So if I write that on the board, that's a big number, right? We'd have a 3, and then that would be followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 meters per second. I think I put my commas in. And so you can see we've got a thousands comma and then a millions comma. So that would be 300 million meters per second. Very, very fast, 3 times 10 to the 8th meters per second. So will light travel faster or slower when it leaves the vacuum of space and enters Earth's atmosphere where there are gas particles? So when light is traveling in the air. It actually does slow down a tiny bit in the air, but we can still use this number, 3 times 10 to the 8th meters per second, for the speed of light in air. In college, you'll learn a number that's slightly different. It's rounded a little differently, so you have more place values that you can use. But for now, 3 times 10 to the 8th is a good estimate for the speed of light in a vacuum or in air. And you need to know that number and memorize it. So when light is traveling in air, it's going almost 3 times 10 to the 8th meters per second. Then if light passes into something else that's clear and transparent that it can travel through, something like water, which is a liquid, would it speed up or slow down when it goes from air to liquid? And hopefully you said that light will slow down. Now this is completely different from sound. Remember that sound actually speeds up when it goes from air to liquid. Sound travels faster when the medium is denser, travels faster in liquid than air, and it travels faster in solids than liquids. But for light, that's not the case. Light is fastest in the vacuum of space, almost as fast in air, and then it slows down as it enters something like liquid, and it slows even more for things like glass or diamond, solid substances that light can still pass through. So light slows down as your medium gets less compressible or more dense, which is sort of splitting hairs for you guys. Gets a little more specific in physics. So when we talk about light, we say that light has wave-particle duality, meaning that it has characteristics of a wave and characteristics of a particle. But it has some differences as well. So you all know light does not have mass, right? So it's not matter, because you learned way back at the beginning of the year that matter is something that has mass and takes up space, and light does not have mass. But it still acts like a particle, which is kind of amazing. And light also behaves like a transverse wave. Actually, two waves traveling together, because there's the oscillation of the electric field and the oscillation of the magnetic field. And so they travel together in the same direction, but perpendicular to the way they're traveling and to each other, right? So light has wave-particle duality. We can see that it behaves like a wave in that it exhibits wave interference patterns. So for the class of 2020, you guys saw some virtual labs where we used water waves as an example when we did it together on Zoom, and you saw wave interference patterns where when waves pass through two slits and then the waves spread out, and you could see places where crests met and added to each other and troughs met and added to each other, and where a crest and a trough met and canceled each other out. That's wave interference. And so it's sort of like when you're jumping on a trampoline and you get it just right and somebody like gets sprung way up high. That's kind of like a wave interference. And light actually behaves like that as well. And when you, I hope, see the lab video I'm going to film later, I hope that you'll be able to see the double slit experiment really well, which shows that when light passes through two slits, it exhibits wave interference patterns as well. And so you should see, instead of just two beams of light passing through two slits and striking the wall in two spots, like you would expect, you actually see an interference pattern of dark and light fringes on the wall. So hopefully you'll see that in the lab, but I've never tried to film in the dark before, so I have no idea how that's going to go. But hopefully we'll find you a video, if I can't get mine to work, where you can observe light showing wave interference patterns. And that indicates that light behaves like a wave. Light also behaves like a particle. So light travels in discrete packets, and that word discrete in this case means that it contains an exact amount of energy. And so light travels in these little packets with an exact amount of energy called photons. And we talked a little bit about how we are protected from things like ultraviolet rays because of certain gases in our atmosphere, which absorb certain types of ultraviolet light that could give us skin cancer, right? Or sunburns. And we talked about how the bond in certain gases, like ozone, contains exactly the same amount of energy as a certain type of ultraviolet light that can damage people's skin. And so when that light strikes the bond in something like ozone and breaks that bond, the UV light is destroyed and the bond in the ozone is destroyed. And it's because the ultraviolet light is electromagnetic radiation, and it comes in discrete packets called photons. And that exact amount of energy is just right to break that ozone molecule apart, and it destroys the ultraviolet light as well. So photons are packets of light, and they can interact with matter like they are particles. But we know light doesn't have mass, so it can't really be a particle, but photons behave when they interact with matter as if they're particles. And one way that is also demonstrated is if you take a piece of metal and you shine light with a high enough wavelength on that metal, then electrons are liberated from that metal immediately. And that's called the photoelectric effect. And it shows that light behaves like a particle striking the metal and causing electrons to fly off of the metal. So those are some ways that we've demonstrated the characteristic of light, that it behaves like a particle. So light behaves like a wave sometimes and behaves like a particle sometimes. And so we say that it has wave-particle duality. And in fact, electrons also have wave-particle duality, which is super interesting, and you'll learn later in your career as a student. So let's see, where are we? Okay, if light does not oscillate in medium, what does it oscillate? So I just said recently that light oscillates a field, right? So we have an electric field and a magnetic field, and electromagnetic waves like light oscillate the electric and magnetic fields. And so that's why they can travel without a medium. They don't have to oscillate a gas or a solid or a liquid. They oscillate a field and can travel through space because there's an electric and magnetic field everywhere in the universe, as far as we know. Key point, when you're asked to explain the theory of what we think light is right now, you need to use the terms electromagnetic radiation or electromagnetic waves, and you need to use the term wave-particle duality. Photons and packets of waves are also really important, so make sure that you practice kind of preparing an answer about what light is, or what wave-particle duality is based on that. So let's see. I'm going to change my board and be right back. Okay, so if we look at the full spectrum of electromagnetic radiation that the sun puts off, then only the teeniest portion of it is light that is visible to the human eye. And I know it looks like a very large section of the spectrum on this drawing, but it's actually a tiny, tiny sliver of the full spectrum of electromagnetic radiation. So the wavelengths of light that we can see range from 400 nanometers to 700 nanometers. You can see the 400 nanometer end of the spectrum is the violet or purple end. The 700 end of the spectrum is the red end. And you all have probably learned the acronym ROY-G-BIV for red, orange, yellow, green, blue, indigo, violet. I've written that backward in the spectrum because I've drawn my spectrum to range from smallest wavelength electromagnetic waves to largest. And so ROY-G-BIV goes backward. It is important for the test to know, let's see, that the red end of the spectrum has the larger wavelength, 700 nanometers. The violet end of the visible spectrum has the 400 nanometer wavelength. If then you build from the visible light that's visible to human eyes, then it gets easier to remember where the small wavelength, big frequency light is, and then where the big frequency, big wavelength, small frequency light is at this end of the spectrum. So we know here at the 400 nanometer end, or the purple end, violet, right? Then the next thing toward the bigger frequency waves is going to be ultraviolet, or the kind of light that gives you sunburn. Ultraviolet light also kills germs, which in these days of COVID-19, if you have an ultraviolet sterilizer, you can sterilize stuff. Then we have X-rays, and then the waves that are given off by the sun with the smallest wavelength and biggest frequency are gamma. You guys learned about gamma when we talked about radioactive decay of atoms, and gamma waves are somewhere around 0.01 nanometers-ish. So that's very, very tiny wavelengths, and they have a very big frequency because, of course, all of these are traveling at the speed of light. So if the wavelength is smaller, the frequency will be bigger. So then if we go from the red end, or the bigger wavelength end of the visible spectrum, the next thing we encounter is infrared, which is basically heat, and then microwaves, which we'll look at in the lab, and then radio waves. And radio waves can be up to 10 meters. And remember, there's almost 3 feet in a meter. And so that's like 30 feet, like the length of a big house, kind of, for the wavelength of one radio wave. So those are very large, right? So when you are trying to focus radio waves with like a dish, that dish can be made of like big mesh, like that's practically, all holes with only a little bit of material, um, like like a screen for a window, except the screen has gigantic holes. Because those wavelengths are so huge, they'll actually strike things, and be reflected anyway, even if there's big, huge gaps in the dish, because of these huge wavelengths. So just remember that the small wavelength, big frequency end of the spectrum is gamma, moving through X-ray to ultraviolet. Then violet is the smallest wavelength of visible light, 400 nanometers. Red is the biggest wavelength of visible light. And then on through infrared, microwave, radio, which has the largest wavelength and smallest frequency. Another interesting tidbit is that just because those are the wavelengths visible to the human eye does not necessarily mean that other creatures can't see other wavelengths. We know that bees, for example, can see ultraviolet wavelengths because if we use camera equipment to examine the types of electromagnetic waves that are reflected from things like flowers, we can see that ultraviolet light is reflected, and there are, in the ultraviolet wavelengths, almost like little runways pointing in the flower, so the bee knows here's where the food is, right along the flower. I think your book may have a picture of an ultraviolet reflective picture of a flower where you can see what a bee might see. And there are other creatures that can maybe see infrared or just outside of the human wavelengths. So let's see. Just remember which end is the big wavelength and which end is the small wavelength. And then frequency, of course, would be inversely related to wavelength. All light travels at the same speed. And in the same medium, right? When we're changing mediums, we may change speeds. So then we have the law of reflection, which says that the angle of reflection is equal to the angle of incidence. So the angle of incidence is the angle at which a light beam would strike a surface that will reflect it, like a mirror. And when it strikes it at any given angle, and we always measure from the normal. So a normal line is a line that's perpendicular to the reflective surface, right? So if you have a mirror here, right, the normal line would be perpendicular, to the mirror. Perpendicular to the mirror, that's the normal line. So a wave that comes in at a given angle with that normal will go out at exactly that same angle, right? So let's say this angle relative to the normal is maybe 40 degrees. Then it will come out also at 40 degrees. We're very used to measuring things relative to the surface that they strike. When we're using light beams, we have to kind of do this counterintuitive thing where we measure from the normal line and not from the surface. Although, of course, this angle is also equal to this angle, since this angle is equal to that, because this is a 90-degree line, right? So that's the law of reflection. Angle of incidence equals angle of reflection. So if I think you have a question somewhere like on your study guide about flat mirrors, and oh, my drawing looks super crooked in the camera. Pretend these two guys are standing at the same exact level as each other. And if you're looking into a flat mirror like we use to just check out our appearance, how much does the mirror have to be the whole length of you for you to see your whole body in the mirror? how short can that mirror be before you would not be able to see both like your head and your feet? So if we think about the angle of incidence being equal to the angle of reflection, we can try to figure that out. Right, so we know light has to strike our eyes for us to be able to see, right? And so there's this little distance between our eye and the top of our head. So we're going to need a beam that goes from our eye to the mirror and then shows us the top of our head. We're going to need a beam that goes from our eye to the mirror and then shows us our foot, right? And so if we look at that, we can see that we only need this piece of the mirror right here to be able to see our whole body, right? Because our foot would be visible basically here and our eye basically here. The way that light is reflected at that angle of incidence equals angle of reflection. And so you need a mirror that's essentially half your height to be able to see your full body in it. Okay, so then a bunch of lab activities in here, and I will come back with how light bends when it changes from one medium like air to another medium like water, for example. Okay, so when light changes from one medium to another, it bends or refracts. And so when I say one medium to another, I mean it goes from air into water, or from water into diamond, or from glass into diamond, or from glass into air. Any change in substance or change in medium will cause light to bend. And this happens because light changes speed. So when it goes from air into water, for example, like our drawing here, light will slow down. And because it slows down, it will change speed, obviously. And then it will bend. So let's see. Light slows down as it goes from gas to liquid to solid, and it speeds back up when it goes from solid to liquid to gas. So every time it changes, and that seems really counterintuitive, right? We think of once something slows down, it's kind of lost energy and it can't just speed back up, right? But that's not how light behaves, right? Light changes speed based on what it's traveling in. So light, say it's here in the air, it hits my window, it will slow down while it's inside the window, but when it comes out on the other side of the window, it will actually speed back up because it's now in air, and it will go the speed of light in air. So when light slows down, it bends toward the normal line, and when light speeds up, it bends away from the normal line. And that's a key point. There's a similar question to this one on the test about how light will bend. So remember that normal line is a perpendicular line between the surface that the light will pass through. And also this is sort of how rainbows are formed, by dispersion of light. So the different colors of visible light have different wavelengths, and that means they have different frequencies. And so violet light will slow down more than the other colors. Red light is least affected by changing medium, and so it will slow down less. And so when they change medium multiple times, they can be spread out enough because of that change in speed that we see them each individually instead of all the colors together added up as a white light. So violet will slow the most, and it also bends the most when it's refracted. So if we look at this diagram, we have a tank of water. So we have air here, water here, and then air again as we're outside of the tank again. So if a light wave comes in and strikes the tank, and then I draw in the normal line, so it's going from air to water, the light wave will slow down in the water. And when light slows down, it bends toward the normal, right? So you can see the light ray in air makes this angle with the normal where I put this red dot. You see that right there. And then when it bends toward the normal, it makes this teeny tiny angle with the normal. I bent it more than it actually would bend. I made it more dramatic. It doesn't bend quite that sharply when it goes from air to water. But I wanted you to be able to see where this reference to the normal is. So we're bent toward the normal, and then it will continue in a straight line through the water until it strikes the air again. So we have an equal to here, this with the normal and this with the normal are equal. Then when it exits the water and enters the air again, we have this angle with the normal, which has gone back to be the same as this one, because light will bend away from the normal when it goes from a liquid to a gas, for example. And so this doesn't tell the whole story, because also some of the light, when it strikes the tank, would be also reflected. So the angle of incidence will equal the angle of reflection, like that. So this and this would be equal. And some of that light would get reflected. Not all of it would pass through into the water. But I just wanted you to see how the light bends when it does change medium. All right, let's see. We will look at, and also the fact that violet light bends the most and slows the most explains why the violet is the inside of the rainbow, right? And then the red is the outside of the rainbow because it slows the least and bends the least. And there are great videos. Hewitt Druitt has a great video on how rainbows are formed. So if you want to YouTube Hewitt Druitt rainbows, highly recommend. Let's see. We're going to look at lenses in the lab. Let's talk about the human eye. So we've been talking a lot about this 400 to 700 nanometer range, right? 400 being violet, 700 being red, that the human eye can detect and see as different colors. But the human eye is pretty remarkable. So we have a lens in our eye that is different than any other kind of lens that you interact with, right? You may use a camera, right? And so when you're using a camera, sometimes you'll see it go and move that lens to a different position to focus it, depending on how far away the object that you're photographing is. And so you can focus a lens by moving the lens's position. With the human eye, our lens stays in the same position, but it's actually a remarkably designed flexible lens that has muscles attached to it, so it can be stretched, and it actually changes the lens's shape so that we're able to focus. If I'm looking at you, I'm focusing close up, and then I want to look across the room, my eye will refocus by stretching and squishing the actual lens inside my eye, which is quite remarkable. Now, I'm nearsighted and farsighted now, but my glasses are for nearsightedness, which means that I cannot see at a distance with good, sharp focus. And so my glasses for nearsightedness are diverging lenses, and I'll show you lenses in the lab that are easier to kind of tell what they are. But, well, I guess I could draw here. So you have a converging lens, like this kind of shape, like a magnifying glasses lens, and then a diverging lens, which is the shape of the lens for my glasses. So you could also call this a convex lens and a concave lens. So convex is a converging lens, and concave is a diverging lens. And so that, since my eye muscles can't quite focus for a distance, these actually cause the light to bend and be able to strike exactly right on the focal point in my eye correctly. So that's kind of the bare bones of how glasses work. But since I'm now of an age, I also can't see close up, so I have to read my lesson plan at arm's length or get bifocals. So I have a lens that focuses for close up and my normal lens that focuses at the distance. But yes, our eyes have a flexible lens that can be stretched and squished, whereas the lenses that we use in the lab are made of, polycarbonate or glass, and they don't change shape at all. We can just move them and change their position to put the right focal point. And we'll talk a lot about colors in the lab, but here's kind of the basic rundown, okay? So our eyes have rods which see light and dark, right? And then we have cones. So always think cone is for color. They both start with CO, right? Cones see color. And we have 3 types of cones, red, green, and blue cones in our eyes as humans. And so they detect red, green, and blue light. And when you mix red, green, and blue light, our eyes send signals to our brain that causes us to perceive a mixture of just red, green, and blue as white light. Okay, and I'll show you, hopefully, if we can get a good dark room and a good video, we can see that in the lab. And as we mix light, it's really different than mixing paint. So you guys probably have some experience mixing paint in art class and the whole like yellow and blue make green thing. And that's great. But remember our eyes, when we're seeing light and not, which is additive primary colors, right? Then we have red, green, and blue cones. So the primary colors for light are red, green, and blue. Right? So primary colors or subtractive primary colors, like when we're mixing paint, are like cyan, magenta, and yellow, the printer ink colors, if you want to think of them that way, right? Cyan, magenta, and yellow. So cyan is like a blue-green, and magenta is like a deep pinkish purpley, and then yellow, of course. So back to light mixing though. So I'll show you some light mixing in the lab video. Okay, but in the lab, when you, I'll have 3 light boxes. I'll have red, green, and blue. When I shine them all 3 together, you'll perceive that as white light. When I mix red and green light, hopefully you can think about that while before you watch the lab video. Red and green light will make what color? That's very counterintuitive. Red and green light actually, well, I won't spoil it. We'll get it in the lab. But and then when I mix green and blue light, what color? And when I mix red and blue light, what color? And as a spoiler, the 3 colors that are produced from those 3 combinations of 2 of the primary additive colors are going to be those printer ink colors, the primary subtractive colors, which is kind of fun. And your test does have some questions, which we'll definitely talk more about in the study guide video with additive primary colors and subtractive primary colors. We'll definitely look at additive in the lab. For subtractive primary colors, these are things like paints and dyes. So you have to think of the subtractive primary colors, right? Cyan, magenta, and yellow. So yellow paint will absorb all wavelengths except for red and green. Okay, so yellow paint absorbs all wavelengths except that it reflects red and green back. Cyan absorbs all wavelengths, but it reflects green and blue back. So when we're talking about subtractive primary colors, if I mix yellow and cyan paint, what will be reflected back? What would I be able to see? So if we think about yellow, right, it reflects only red and green. And if we think about cyan, it reflects back only blue and green, right? But that means yellow is going to absorb the blue and cyan's going to absorb the red. So the only one that we're going to be able to see that both of them reflect when they're mixed together is green. So a mixture of yellow and cyan will produce a green color. And remember, this is mixing paints and dyes, totally different than mixing light. Right, because this is what is being reflected from those paints and dyes, not what the light mixing is going to produce. So, yeah, the study guide will cover that a good bit more, and we will talk about that in the lab, well, at least additive primary colors in the lab. For subtractive, definitely look at that section of the book carefully before the test. All right, so I'll be right back with a study guide video.